Study along with Melissa, Lucy, and I as I teach her and you everything you need to know about electron affinity. Before we get started though, make sure to download your free study plan using the link in the description. All right, grab your periodic table and let's begin. All right, so for electron affinity, it's going to be a little bit different from like ionization energy, because ionization energy, we were removing an electron. Now for electron affinity, we're actually gaining an electron or like adding an electron. And you're gonna notice that the actual formula is reversed, or it's different here, because this like 1 plus electron is now on the reactant side or left side instead of the product side or right side, like we saw before with ionization energy. And we're no longer forming a cation or positive charge, we're forming an anion or negative charge. All right, so in this case, we're going from like an atom, so like chlorine, in its gas state, or adding an electron, and then that becomes an anion. So that's the concept of electron affinity. It's gonna have the exact same trend, where we're gonna increase as we go from left to right, and then across a row or across the periodic table, and then it's gonna increase as we move up a column. So luckily these are gonna be easier to remember because they're really the same sort of trend. And let's talk a little bit more about some of the things they might say or ask for. I would say, like, if they're asking for definitions, something to definitely know is just, well, what does this actually mean? We said that it's energy that is being released. So keyword there is released. Now, whenever energy is being released, there's a keyword that I want you to understand and to start to kind of like pick up. And it's said to be exothermic. So an exothermic reaction just means that energy is being released. That's all. Okay. So that's what that means. So in case you were to see, oh, is electron affinity exothermic or endothermic? Well, it would be exothermic because it's releasing energy. And endothermic just means you're absorbing energy. But you're going to learn that later on this semester. But for now, okay, just knowing, okay, releasing energy, that's exothermic. And that's what electron affinity is. So cool. The more energy that is being released, the larger the electron affinity. And let's just do an example. Looking at our trend again. So I have an A, which is here, our B, which is here. Just looking at the trend, which one would be the largest or have the highest electron affinity?
Sodium.
That's it. I love these. Yes, they're so much easier. Following the trend. But that's never for long, because there are exceptions to this as well. I know. So with this one, it's now going from 1A to 2A and 4A to 5A. So those are the ones that I would say to know. And then I actually went ahead and just wrote out what the electron affinity would actually be numerically. So that's what you're seeing here right now with all of these values. And then, by the way, I know this is kind of like opposite from what we learned in math, that like, oh, well, if something is 0 and if I had like negative 200, which one is larger? Isn't it the positive value? But in this case, for electron affinity, because we're looking at energy released, that's negative. So we're actually looking at the highest negative value. So like the higher the negative value that we have, the more energy is going to be released, and that's going to be the highest electron affinity. Okay, so that's what I want you to think of. So if you were to ever, if you were given any negative value, the higher negative value is going to tell us that it is the highest electron affinity. Okay. Doesn't matter if it's positive, we don't want positive here. And the reason for that is because if we're gaining an electron, then it's becoming more negative, right? The more electrons that you start to gain, then that means we're actually going to have, more of a negative charge. So let's see what else with this. Our exceptions from 1A to 2A are going to be the opposite. So 1A is actually going to have a higher negative value or a higher electron affinity. So this is higher. And then our 2A would be lower, which I have here, but I'll write it again. The reason for this is because the electron that was just, and you know what, I kind of want to just show it here. let's show it. It's going to make so much more sense here. We're going back to orbital diagrams. And no, you don't have to draw this out. It's just understanding why the exception is what it is, going from 1A to 2A. So if I were to just draw out lithium, looking at that orbital diagram, and I'm just adding an electron, right? I'm adding an electron to the last orbital that I have to fill. So, okay, I just added this one electron. And that's happier, right? That's happier. I know, okay, great, it's now full. And if I were to compare beryllium, which is next to it, then I would see, well, I'm adding one more electron again. And if you know, the electron configuration for lithium was 1s2, and then 2s1. Beryllium was 1s2 and 2s2. So this was already full. Yeah, this was already full. And then next, if I added one more electron, now this is actually introducing a p orbital, which is what I have to add next, because this is completely full. I can't add another electron. This is not allowed to be 2s3. Instead, I have to actually turn this into a p orbital, and I just added an electron. So the reason for this is if the electron that was just added has to go to our p orbital instead of the s orbital, which is what I just showed here, right? This has to go to the p orbital, then that means that our electron is even further away from the nucleus and then would feel more repulsion with all the other electrons surrounding it. So like if this is our nucleus, and this went from, instead of it being like, oh, our electron is going to be here. Oh, no, it's not. It's no longer S, it's actually P. So now this is even further away from that nucleus, and whatever electrons are, surrounding, then it's going to feel more repulsion than that attraction to the nucleus. So then that's why it's not going to really give us that much energy. Making some sense. Okay. And yeah. And again, it's really just knowing the exception. So same sort of concept here, going from 4A to 5A. 4A is actually going to have a higher electron affinity versus our 5A, which would have a lower electron affinity. Now, if I were to once again look at the orbital diagram, I would see that, well, if I added an electron to carbon, then that means I would add the electron here. So this is half full now that we added one electron to that 2p orbital. And then now for nitrogen, that's actually a little bit like this was already half full and we added one more electron here. So basically what's happening here is that nitrogen would have a lower electron affinity because it's going to an orbital that's already occupied. So therefore it's going to have more repulsion here. So main thing I really want you to just focus on, because I know this is like really technical, talking about electrons and repulsion and whatnot, is just understanding, hey, this is going to be a higher electron affinity, this is going to be a lower electron affinity, and it's going to be based on where those electrons are going in our orbitals. That's essentially the concepts here for these exceptions. It's basically saying, hey, maybe it's not going to, it's going to an orbital that's even higher in energy, and then it's actually going to be further away from the nucleus. That's essentially the concept.
Okay. And is it only when we're comparing like 2 again?
Yes. Yeah. So 4A to 5A and 1A to 2A.
Got it. Okay.
Cool. Okay. I want you to try this out now.
Okay. So I don't have it memorized yet, so I'm just going to put it on here. Mm-hmm.
Good.
That one and
4A to 5A. So 4 would be carbon, and then 5 would be that nitrogen column.
Okay, thanks. Mm-hmm. Okay. Oh. So B. If the electron affinity is increasing as we go, across that way, mm-hmm. and it's asking the more negative electron affinity, then wouldn't it be B?
So for negative, electron affinity should be negative is basically it. So don't let that throw you off. If they were to actually give you values For everything, that's kind of why I included the more, and this actually is a possible question for them to put, more negative electron affinity. So if they like, instead of giving you like the actual elements, if they just gave you one element is negative 141, another element is 0, then you would pick the more negative electron affinity.
Okay.
So I just want you to focus on the trend here.
Got it. Okay, so sulfur.
Yeah.
Okay. Cool. So now we are looking at sodium and magnesium.
Good.
And this is the exception.
Mm-hmm.
So it's going to be sodium.
Good.
And then Si, is that silicon?
Correct.
Phosphorus. So it's going to be silicon.
Yes.
And lithium. And here's... Oh, is that fluorine? I'm trying to like remember to say the names.
Good. That's fluorine, correct.
Okay, cool. So it's going to be fluorine.
Correct. That's it.
Cool. Okay, that's not that bad. It's kind of the same thing. You know, I think what's tripping me up, and I appreciate you explaining it to me because I need to like understand it, because a lot of times he will ask us questions to check for understanding. That's like the hardest part, you know, of everything is like actually understanding, but why?
Right. The concepts. Yeah.
Yeah.
And they're complicated.
It is.
I would honestly say they're really complicated, especially this, because you haven't learned everything enough, I'd say, to truly understand every little detail of this.
Right.
And like even like some classes, like you won't get into it until you get to the next class of chemistry or the next level. And it's like, and I can't teach you that right now because you haven't even gone through the basics, So it's like I'm kind of trying to outline a little bit, but I don't want you to, if not every little detail makes sense, it's not expected of you.
Right.
Yeah, because you're not going to learn this until later on, if you even decide to. Like,
Yeah, no, that's good to know though.
Yeah.
Because this gets like really deep.
No, it does. It does. And even as like when I was a chem major, going from this is the beginning class, they'll even kind of later say like, oh, well, forget certain things that you learn in Gen Chem 1. Like, we're going to build on this or completely change and say why that was incorrect. And it's like,
Oh my gosh.
Thanks for that.
Yeah, thanks. That's great.
Yeah. So it does. I know it builds, and there's a lot to it. Trust me. I know. But as long as this is making sense and you can answer these questions, I think you'll be fine. If you're feeling overwhelmed and stressed, you are not alone. I know that Melissa Lucy right now is currently feeling that way too, but she's pushing forward, she's moving forward, she's really trying to just study. And she's realized that it just takes a lot of practice, and that's completely true. A lot of this is just going to require you to sit down and put in the effort, put in the time, and practice and review. That's really what a lot of this is. So keep putting in that effort, do your best, because I know you're capable.